Right now, a person sitting in Chicago picks up a phone to start a voice call. Their voice must reach someone thousands of miles away in Berlin in a matter of milliseconds. To make that journey, the digitized audio travels as physical light pulses, fired through submarine cables resting on the floor of the Atlantic Ocean. Inside those cables are strands of glass fiber, each thinner than a human hair, carrying terabits of data every second. But light alone is just noise. To be understood by the receiving machine, those pulses require strict organizational rules. We see these rules through encapsulation. Application data is wrapped inside a transport header, then wrapped again inside an IP header. Looking specifically at that transport layer, its entire job provides the handling instructions needed to direct the payload to the correct application. At this layer, the Internet relies entirely on two different protocols, UDP and TCP. They solve overlapping problems, but they operate with completely opposing architectural philosophies. By opening up the exact bit-level structure of their headers, we can see the strict engineering trade-offs required to balance speed against perfect reliability. We start with the simplest answer. This animation illustrates the User Datagram Protocol, or UDP. It is a stateless, fire-and-forget protocol designed to launch data into the network as fast as possible without waiting to establish a connection. We can see this minimal overhead in the UDP header diagram. It is a flat, rectangular grid exactly 8 bytes, or 64 bits, wide, divided into 4 equal 16-bit quadrants. The top 2 quadrants handle multiplexing. They define the source port and the destination port. Because a machine might run dozens of applications simultaneously, these numeric values ensure the data reaches the correct specific process, rather than just the general machine. Moving to the lower left, the length field simply specifies the total size of the datagram, combining the 8-byte header and the payload. Finally, the lower right quadrant holds the checksum. This is an error detection mechanism. If the data is corrupted in transit, the calculation fails and the receiver silently discards the packet. And that is the entirety of UDP, 4 fields, 8 bytes. It provides the absolute minimum required for application routing, actively sacrificing any guarantee of delivery in exchange for maximum velocity. But speed is not always the priority. Physical networks are chaotic. Fiber optic links degrade, router buffers overflow, and packets are routinely dropped, duplicated, or delivered out of sequence. To solve these physical failures, the Transmission Control Protocol, or TCP, requires a significantly larger footprint. As this structural grin expands, we see a minimum 20-byte header, dwarfing the previous UDP model. TCP introduces reliability first through the sequence number. This massive 32-bit row assigns a specific position to every single byte in the stream, allowing the receiving machine to reassemble packets in the exact correct order regardless of when they arrive. Directly beneath it sits a second 32-bit row, the acknowledgement number. This establishes a cumulative confirmation system. The receiver explicitly states which bytes have arrived successfully, and if a sender's timer expires before receiving that confirmation, it automatically retransmits the missing data. This architectural approach was designed by Vint Cerf. He partnered with Bob Kahn to engineer the specific reliability mechanisms to handle the chaotic realities of early internetworked computing. By adding these two 32-bit fields, TCP forces a chaotic physical network to behave like a perfectly ordered, mathematically verifiable byte stream. Because the TCP header can vary in size, depending on added options, this 4-bit data offset field acts as a boundary marker, telling the receiver exactly where the instructions end and the payload begins. But the state of the connection is driven by the 9-bit flags field. These are literal Boolean switches, toggle bits labeled URGE, ACK, PSH, RST, SYN, and FIN, that dictate the exact mode of communication. 2 of these switches, the SYN and ACK flags, manage the sequence number synchronization we discussed earlier. As shown in this schematic, they drive the 3-way handshake. Before any data moves, the client sends a SYN packet, the server responds with a SYN ACK, and the client confirms with an ACK. Both sides now agree on their starting sequence numbers. This handshake ensures mutual readiness, but it demands an entire round trip of latency before a single byte of actual application data can be transmitted. TCP's final structural requirement solves flow control. If a powerful sender transmits data faster than a slow receiver's memory buffer can process it, that buffer overflows and data is permanently lost. To prevent this, the TCP header includes a 16-bit window size field. Every time the receiver acknowledges data, it uses this field to advertise exactly how much buffer space it currently has available. If the receiver's buffer is completely full, it sends a window size value of 0. As we see in this fluid dynamics model, that 0 acts as a hard physical stop command, closing the valve and halting the incoming data flow immediately. To support modern high-bandwidth connections, an additional variable options field can apply a scaling multiplier to this limit, allowing the window to expand massively on fast, high-latency links. TCP's 20 to 60 byte size is the direct result of strict engineering requirements. It is the necessary overhead to enforce connection state, exact ordering, error recovery, and flow control. We can now see the clear structural divide. This split screen compares the complex, fully populated 20-byte TCP header against the minimal 8-byte UDP header, visualizing the trade-off between strict statefulness and raw speed. TCP is used when a single missing byte is catastrophic. It powers HTTP web traffic, SSH secure shells, financial transactions, and BGP routing updates. UDP is used when an out-of-date packet is worse than a dropped packet. It drives DNS queries, DHCP address assignments, VoIP calls, and live multiplayer gaming. Right now, inside the server racks of massive data centers, these two protocols are executing trillions of times per second. Neither is superior. They are complementary tools engineered to enforce opposing requirements over the same shared physical network. Every email, video, and voice call functions strictly by encapsulating physical light pulses inside these exact 8-byte and 20-byte rule sets. The core philosophy of this transport layer architecture remains unchanged since it was designed for the networked mainframes of the 1970s, yet it is so durable that it currently routes data to the absolute edges of human infrastructure, extending reliable communication to the International Space Station. Every time an application connects, it makes a deliberate choice between TCP's mathematical reliability and UDP's uninhibited speed. The microscopic architecture of these headers is the invisible logic holding the modern digital world together.